Okay, so a new video of the classical field theory. We will begin from where we left last time. So last time we saw a new method of synchronization. So we need to synchronize clocks using a universal constant, which is the speed of light. And we found that this line of synchronization is given by the line of equation t equals Vx. And t equals Vx is symmetric to x equals Vt with respect to x equals t. So the consequence, as we said last time, the consequence of the synchronization is that if you have two simultaneous events in a certain frame, they will not be simultaneous anymore in other frames, even if they were inertial frames. So this is a real synchronization of clocks. We have to synchronize our mobile clock with the line t equals Vx, which corresponds to t prime equals 0. So this new line is the x prime corresponding to the mobile frame r prime, and this line x equals Vt corresponds to t prime, which is the time axis of the second frame, the mobile frame. So if you can see, x prime and t prime are tilted with respect to x and t because they are, or the mobile, the origin is moving with a speed v. Of course, these angles are exactly the same and equal because the lines are symmetric with respect to x equals t. So we will use this new synchronization from now on throughout the entire course. So when I tell you that two clocks are synchronized, it means that they are synchronized with a ray of light, a real synchronization. Now we need a new transformation of coordinates to go from one frame to another frame. So if you have a frame R and a frame R prime in such a way that R prime is a uniform translation with respect to R, we need to know the coordinates or the transformation of coordinates from R to R prime or from R prime to R. Let me remind you of the old transformation, the Newtonian transformation, which tells us that x prime equals to x minus Vt, and that the time is absolute, that t equals to t prime. This is the Newtonian transformation as we saw it in the last video, which is always true and applicable for low speeds. And it has been true for over some 3 centuries now. And it is always applicable at low speed. The only error we see in this transformation, or the only disadvantage of this transformation, Newtonian transformation, is at high speeds. So for speeds that are very high, that are close to the speed of light, especially for the light itself at the speed c. We see that the Newtonian transformation fails to describe the motion at high velocity. So since it is always true at low speeds, so our new transformation should not be completely different from the Newtonian transformation. We should use this Newtonian transformation and to bring some correction to the Newtonian transformation to make it true at high speeds. So we don't need to remove completely the Newtonian transformation and to invent a new one. We just use the Newtonian transformation, and we need to bring some corrections to make it applicable on high speeds. So the Newtonian transformation is not completely false. It's an approximation for low speeds. Now we need to find the real and true transformation that is applicable to all speeds. So we will consider our old transformation x prime equals x minus vt. We will take this equation and multiply it by a function f, which is of course a function of v, since our variation is related to the speed, to the displacement at a speed v, or to the motion at a speed v. So our function f should be a function of v. The transformation should be, in this case, x prime, x minus vt is the old transformation, multiplied by a certain function f of v. And we know that when t prime equals to 0, t equals vx. So if we take t minus vx, it is also equal to 0. So it is also equal to t prime. So we can replace t prime by, or we can say that t prime is equal to t minus vx, which is also 0, times a certain function g of v, g of v. G of v is also a function of v, since our variation is related to the speed v. So t prime, in this case, is not equal to t as in a Newtonian transformation. T prime is equal to t minus vx multiplied by a certain function g of v. So you can see we are starting to write equations where you can see that t prime is not exactly equal to t. This is the beginning of our new transformation. We also know that the speed of light is the same everywhere. So x equals to t and x prime equals to t prime. And in a certain frame where c is not equal to 1, you can say that x equals to ct and x prime is equal to ct prime. Okay, we will use the case where c is equal to 1. So you will take x equals t and x prime equals t prime to make our calculation. So we have two new equations. X prime is equal to x minus vt times f of v, and t prime, which is equal to t minus vx multiplied by the function g of v. We need at least for array of light, we need x prime to be equal to t prime and x to be equal to t. So if x prime is equal to t prime, we need f of v to be equal to g of v. Otherwise, x prime will not be equal to t prime. So f of v is equal to g of v. F of v is equal to g of v, so our equations become x prime is equal to x minus vt multiplied by f of v, and t prime is equal to t minus vx multiplied by also the same function f of v. So now we need to find this equation or this function f of v. To find it, we will use exactly the same calculation as it appears in the first paper of Einstein, when he published his theory of special relativity in 1905. This first paper contains this calculation of how do we find this function f. Before calculating this function f of v, we need to define some parameters. At first, we all know that in inertial frames, so the frames that are in uniform translation, one with respect to the other, it is impossible to know which frame is in motion. So it is impossible to say or to know if r prime moves with a speed v with respect to r, or if it is r that moves with a speed minus v with respect to r prime. An inertial frame, it is impossible to say because there is no acceleration. You cannot measure accelerations of the frames, so you cannot say which one is in motion. So R prime has a speed v with respect to r is the same as r having a speed of minus v with respect to r prime. It's the same. It's the same, exactly the same condition. There is no measurements in physics that lets you tell which one is in motion. So our transformation in this case should be symmetric. What do we mean by symmetric? It means that if you have x prime is equal to x minus vt times f of v, you should also have x equals x prime minus v t prime times f of v. And if t prime is equal to t minus vx times f of v, your t should also be equal to t prime minus vx prime f of v. This is what we call a symmetric transformation in inertial frames that lets you go from r prime to r or from r to r prime. We need it to be a symmetric transformation. So we will apply the simple and most evident calculation, and we replace each term by its equivalent. So x is equal to x prime. So we replace x prime by x minus vt times f of v plus v t prime. We replace t prime by t minus vx times f of v times f of v. So we have x minus vt times f squared of v plus vt minus vx times f squared of v. So if we expand this equation, we have x times f squared of v minus v squared x f squared of v minus vt f squared of v plus v t f plus vt times f squared of v. So you have minus vtf squared plus vtf squared. These two terms are cancelled. You will get x times 1 minus v squared times f squared of v. Of course, x should be equal to x. Otherwise, it will be a disaster if x was not equal to x. So if we are in this universe, in this normal universe, we have x that should be equal to x. So this quantity should be equal to 1. So 1 minus v squared times f squared of v is equal to 1. So f squared of v is equal to 1 over 1 minus v squared. So our famous function f of v is equal to the radical of 1 over 1 minus v squared, or it is equal to 1 over the radical of 1 minus v squared. Of course, we are taking the positive radical. There's no sense to take the minus sign here. It has no physical meaning. So our new transformation is x prime is equal to x minus vt times f of v. So it's times 1 over radical of 1 minus v squared. So it's x minus vt over radical of 1 minus v squared. And t prime, which is t minus vx, times f of v, so it's t minus vx over the radical of 1 minus v squared. These two equations are called the Lorentz transformation. This is the transformation of relativity in inertial frames. It is called the Lorentz transformation. And we will use it through this course, the entire course. So you have to put it in your mind, in your head, This is the Lorentz transformation. If you are writing this equation in a frame where C is different from 1, so we need to correct the form by arranging the dimensions. So let us recall the dimensional analysis that you saw in the course of classical mechanics of the first year. The dimensional analysis that tells you that both sides of an equality should have the same dimension. So if you have a length from one side, you should have a length from the other side. If you have a time on one side, you should have a time on the other side. So if you have x or x prime, which is a length, v times t is always a length because it's a velocity multiplied by a time. So it's meter per second multiplied by second. You simplify by the second, you will get the meter. So the quantity v times t is always a length. It has a dimension of length. So x and vt, or x prime and vt prime, they all have the dimension of length. So if you have v squared, if you divide v squared by c squared, you remove the dimension. So you are dividing a velocity squared by a velocity squared. So the dimension or the units are simplified. You will get a quantity with no dimension. So radical 1 minus v squared over c squared, this denominator has no dimension. So x prime is a length, x minus x is a length, vt is a length, so length is equal to a length, so there's no problem here. The denominator, when you divide v squared by c squared, it has no dimension, so you have a length that is equal to a length. So we just divided by c squared. When you go to the time, okay, from this side you have t prime, which is a time. So the second side of the equation should also be a time. You have no problem with the denominator, which has no dimensions. You have 1 minus v squared over c squared. It has no dimension. T has a dimension of time. We have v times x. If you divide v times x by the square of a velocity, so all the lengths will be simplified. You can simplify it by the meter. You will get only a second here as a unit. So this quantity has a dimension of time. So t is time, vx over c squared is time. So this side has a dimension of time, and t prime is time. So your dimensions or your equation is dimensionally correct. So this is a form of the Lorentz transformation and a frame where c is different from 1. X prime is equal to x minus vt over the radical 1 minus v squared over c squared, and t prime is equal to t minus vx over c squared over the radical of 1 minus v squared over c squared. I think you saw this form last year in the course of modern physics. In this course, we will in most of the cases we will use as a frame where c is equal to 1. So we will need the form with the radical of 1 minus v squared. We will not use the v squared over the c squared. So in this case, it is like if we are measuring the speeds by the unit c, which is the speed of light. So when they tell you that a speed is 0.5, for example, if you see it in a book or in a reference, when you see a speed is equal to 0.5, it means it is equal to 0.5 c. So we are measuring now the speeds with the unit c. So V is equal to 0.5 means that V is equal to 0.5 C. Sometimes V is very, very low. So if V is very much less than C, so the quantity V squared over C squared will tend to 0. So your denominator will be 1. And V squared over C squared is 0, and this quantity over C squared is also 0. So we'll get back to Newton, because T prime would be equal to T. If this tends to 0 and this tends to 1, so T prime would be equal to T. And if the denominator is equal to 1, x1 would be equal to x minus vt. So we will go back to Newton. So for low speeds, Newton is always true. If you have V over C is 0.1, which is not very slow, your V squared over C squared is also smaller than 0.1, which is 0.01. So you can see that the quantity V squared over the C squared is a very small quantity if V is small. So Newton was not wrong. Newton's equations are always applicable, always true at low speed. This transformation, our new transformation, is only necessary at high speeds, or for speeds approaching the speed of light c. In our case, y and z are invariant since we are taking frames that are in translation with respect to c. So the only variation is along the x-axis. So y and z are always invariant in our case. If you are moving along y, so y would be, so the variation would be along y. If you are moving along z, your motion would be along z and the variation would be along z. But for simplicity and to make the calculation simple and easy, we always take the translation along x. So in reality, we are working in a plane x and t, because y and z are the same, they are invariant. So the only variation is in terms of x and in terms of t. So we are working in a plane defined by x and t, which we will call the space-time. So the space-time is a plane of x and t. A simpler form of Lorentz equation is the form that I think you saw last year, when you replace 1 over the radical of 1 minus v squared by the symbol gamma. So gamma is 1 over this radical, and v over c is beta. So you can simplify your equation by replacing by gamma and beta. Of course, gamma is a dimensionless quantity because v squared over c squared has no dimension, and 1 you don't have any dimensions. So gamma is dimensionless. If you find gamma in an equation, it indicates a dilation because gamma is bigger than 1. You see the denominator is less than 1. It's 1 minus something. So 1 over a quantity which is less than 1. So gamma is always greater than 1. If you see gamma in an equation, it means you have a certain dilation. So your quantity is becoming bigger and bigger. If you have the inverse, if you have 1 over gamma in an equation, it means that you have a contraction. So your quantity is becoming smaller with the speed. Here are some numerical examples. If beta is equal to 0.7, so if beta is equal to 0.7, it means the velocity v is 87% of the speed of light. So the speed is 0.87 c, or 87% of the speed of light. In this case, gamma is 2. So if your quantity is dilating, it will become a double quantity. If it is contracting, it will become a half the quantity. If you have beta equals to 0.99, so if you are moving at 99% of the speed of light, which is possible in certain accelerators, electron accelerators, we are able now in certain accelerators to accelerate electrons at 99% of the speed of light. In this case, your gamma becomes equal to 12. So you are dilating quantities by 12, or you are dividing your quantities by 12. This will be applicable to time and length. Let's see the example of the contraction of lengths due to this motion at a speed. We will consider a mobile observer that is viewing a 1 meter long object that is placed at rest in a frame R. So you have your frame R, which is X and T. On this frame, you have a 1 meter long object placed in this frame. So you have one end is at 0, and you have one end is at X equals 1. So you have this object. The length is 1 meter, let's say, or any unit of length. You have a mobile observer that is moving with a speed v. So if you have a frame attached to this observer, this frame would be these two red lines. So t equals vx, which corresponds to x prime, and x equals vt, which corresponds to t time, which they are tilted with respect to x and t, as we saw in the synchronization of clocks. So the mobile frame, you have an observer moving at a speed v. He needs to measure the length of this 1 meter object. So he needs to detect the two ends of the object and to calculate the length. If he detects the two ends of the object at two different instants of time, his measurements would be completely false. Because as we saw it in the synchronization, to make a real and true measurement, you need to detect the two ends of the object exactly at the same time. Otherwise, your measurements would not be synchronized, and your measurement will be completely false. So this observer, this passing observer, this mobile observer, he needs to observe exactly the two ends of the object at exactly the same time. So in the mobile frame, if the first end is at O or at 0, the second end is at point A. So if your observer is making the measurement at t prime equals 0, for the mobile frame, for the mobile observer, the time is t prime. So if he decides to make the measurement at t prime equals 0, he detects the two ends of the object at t prime equals 0. So t prime equals 0 corresponds to this point A. So what he is really measuring in his own frame or prime, in his mobile frame, is OA, because for him, the second end of the object is at point A, because this is the point that corresponds to t prime equals 0. So let's find this distance OA, which is x prime, which is the distance, the length in the frame, in the mobile frame R prime. We know that in the frame R, x and t, point A is at x equals 1. If you see the coordinates of A and frame xt, so it is at x equals 1, which corresponds to the trajectory of the object in x and t, because the object is at rest, so it always has a length of 1 meter, and as a function of time, it is always at the same position. So its trajectory is a line that is parallel to t, because it is at rest. So at any given time, t is at x equals 1. So point A has an x equals to 1. And in the second frame, it corresponds to t prime equals 0. According to Lorentz transformation, t prime is equal to t minus vx over radical of 1 minus v squared. Since for point A, t prime equals 0, so t minus vx is equal to 0 in this case, so t equals vx. So we know that A corresponds to this line of synchronization, which is the axis x prime. X prime, according to Lorentz, is equal to x minus vt over radical 1 minus v squared. So if we replace t by vx for point A, so we replace t by vx, we get x minus v squared x over radical of 1 minus v squared. Or also for point A, x is equal to 1. So this is 1. So it's 1 minus v squared over radical of 1 minus v squared. It is equal, finally, to radical of 1 minus v squared. Radical 1 minus v squared is 1 over gamma, which is less than 1. So if x is equal to 1 meter, you see that x prime is less than 1 meter. So for the mobile observer, the object has a length of less than 1 meter. It is shorter. So you have, due to the motion at a speed v, you have a contraction of the length according to this new transformation of Lorentz. The mobile observer sees an object which has a length that is less than 1. So you have a contraction of the length. Is it magical? No, it's not magical. Is it I don't know. It's magic. It's not magic. It's not something that is so weird. It's not a weird stuff. It's not like ghosts or something. In reality, it's so simple. The two observers are measuring two different points of space of time. The observer at rest is measuring from point O to this point that corresponds to 1. The mobile observer is measuring from O to point A. So the ends of the object are placed in two different points of space and time according to each observer. So the second end of the object is here with respect to an observer at rest. And it is here at point A for an observer moving at a speed v. So they are measuring, they are detecting two different points of space and time. It is the same object, it has always the same length at rest, but due to the motion at the speed v, the second observer is detecting a different point in space and time. That's why he sees a shorter length. So it's not magic, it's physics, it's relativity. This is how you should wire your brain in such a way to imagine this phenomenon. Let's see about time. So what happens to the time? We will take a clock, a mobile clock, moving with a speed v. So it is moving on this red trajectory on x equals vt. So if your clock, your mobile clock tells you that the time is equal to 1 second, which means t prime is equal 1 second. So what is t? If t prime is equal to 1 second in the mobile frame, what is the time t in the frame at rest? Of course, we will use the Lorentz transformation. We will always use the Lorentz transformation. There is no other way than the Lorentz transformation. So keep it in your mind. Just stick it to your mind, this Lorentz transformation. If we use the Lorentz transformation, giving our conditions that t is equal to 1, t prime, sorry, is equal to 1, for x prime is equal to 0, because this red line, which is t prime, corresponds to x prime equals 0. So when, for the point where t prime is equal to 1, also we have x prime is equal to 0. If you take the equation of t, so as t is equal to t prime, which is 1, minus vx prime, which is 0, here you have a minus, or plus, it's a 0, so it doesn't matter. So t is equal to 1 over radical 1 minus v squared. 1 over radical of 1 minus v squared is the quantity gamma, which is greater than 1. So if your t prime is equal to 1, your t is greater than 1. This is the dilation of time. Here, this is the origin of the twins paradox. So you know the history of the twins, which is a fictional story. If you take two twins that have exactly the same age, you put one of the twins on a space shuttle that goes around the space at a speed v for a certain time. And if this twin comes back to Earth, if you compare the two twins, you will find that the twin that stayed on Earth is older than the twin who traveled through space at speed v, because of the dilation of time. Now you will tell me that t is greater than t prime. So how is t prime dilated? Don't look at the number. Don't look at the number. Look at the time or the space between two steps of time. What we mean by time dilation is that the clock is moving slower. If the clock is moving slower, so it will give you a measurement of a shorter time, because it will tick slower, so it will tick less. So t prime is less than t. So if your clock is ticking slower, the time is dilated. What do we mean by a dilating or a dilated time? A dilated time means that the clock is ticking slower. So it gives you a smaller number of seconds. So this is the dilation of time. So the smaller number of seconds corresponds to a dilated time. So that's why t is bigger than t prime. This is why the twin at rest gets older than the twin that moves. So you have to understand it in this way to understand the dilation of time. Okay, we will see now what we call the space-time interval. If you are in a classical space, in a Euclidean space, the shortest distance between 2 points of space is a straight line. So if you are working in a Newtonian space, what we call a Euclidean space, a straight line is the shortest distance between 2 points of space. So is it always true in relativity or in space-time, in xt? We will see about that. Let us consider two spatial frames, x, y. I will go back to spatial frames, x and y, not x and t. If you choose two frames, x and t, and x prime and t prime in green, they have the same origin. The two frames have the same origin, and x prime, y prime is rotating around x and t. So the axis of rotation passes through O, or the origin. So they always have the same origin, and x prime, y prime is rotating around x and t. If you take a point in space, which is this red dot, which represents a point in space, it has two different sets of coordinates. And the first frame, on the blue frame, it has coordinate x and y. On the green frame, it has coordinates x prime and t prime. So two sets of coordinates, x is different from x prime, y is different from y prime, but you have a quantity that is always invariant, which is the distance from the point to the origin, this red line. This red line is the same no matter the frame. So it is the diagonal of this blue rectangle or this green rectangle, or it is the hypotenuse of this blue triangle or this green triangle, which is equal to x squared plus y squared, which is the same if you take it as x prime squared plus y prime squared. So this red line is the same if you measure it in xy or if you measure it in x prime, y prime. It is what we call an invariant quantity. This quantity is independent of the frame. So in all frames, this hypotenuse or this diagonal is the same. It is equal to x squared plus y squared. Is it invariant in space-time? We need a similar quantity. We need a quantity that is similar to x squared plus y squared. And we need it to also be an invariant of space-time. Because if you are making a physical law, you need it to be an invariant. You need it to be independent of the frame. Otherwise, it would not be a physical law. If you need to make a law of physics, you need invariance. If you don't have invariant quantities, you don't have a law of physics. Keep it in your mind. Stick it in your mind. If you don't have invariant quantities, you cannot make a law of physics. Laws of physics are always based on invariant quantity. So let us find this invariant quantity in relativity or in our space-time x and t. Let us just try by analogy to a Euclidean space. Instead of taking x squared plus y squared, Let's try with x squared plus t squared. Is it equal to x prime squared plus t prime squared? If you use Lorentz, you replace t prime and x prime by their values with the equation of Lorentz, t minus vx squared and x minus vt squared. If you replace, you will see that this equality is unchecked. It is not true because you have minus 2 vtx minus 2 vtx that doesn't cancel. So this equality is not true. So the quantity t squared plus x squared is not an invariant of space-time. You cannot use it to define physical laws. So we need another quantity. It's not that difficult because if you have minus 2 vtx and minus 2 vtx, so if you put a minus sign here, you can cancel these quantities. So let us try with the quantity t squared minus x squared. Is it equal to t prime squared minus x prime squared? Let us see. So this is t prime squared minus x prime squared. If you put x squared as a common factor, you will get v squared minus 1. And if you put t squared as a common factor, you will get 1 and minus v squared. And minus 2 vtx minus times minus, so plus 2 vtx. So these two quantities are cancelled. You will get this equation, x squared times v squared minus 1 plus t squared times 1 minus v squared over 1 minus v squared, which is equal to t squared minus x squared. If you put the minus sign outside, you will get, and you simplify by 1 minus v squared. So you will get minus x squared plus t squared, which is of course is equal to minus x squared plus t squared. So this equality is verified, is checked. Our invariant quantity in space-time is simply the quantity t squared minus x squared, or x squared minus c squared. It is the same. You can use both of them, x squared minus t squared or t squared minus x squared. It is the same. They are both invariant by the Lorentz transformation. This quantity is a distance, or it is the distance, if you go back to this drawing, the distance from 0 to this red point in space-time is the quantity t squared minus x squared. So this invariant quantity represents of the distance to the origin in space-time. And you know that x and t are not invariant by themselves because x is different from x prime, t is different from t prime, but the quantity x squared minus t squared is the invariant. So it is a distance in space-time. So you will tell me that this distance has a minus sign. So if t squared is greater than x squared, you will have a distance that is negative. Yes, you can have a distance that is negative because we are working in space-time in a non-Euclidean space. This would be impossible in a Euclidean space, in x and y. But in x and t, in a non-Euclidean space, it is possible to have a distance that is negative. We will see this condition in more details in the next videos. So don't be surprised don't see it as a miscalculation. You can get in space-time and a non-Euclidean space a distance that is negative. So just remember that we are working in a 4-dimensional space that is very difficult to draw in a 2-dimensional whiteboard or paper. You have to imagine it. So just you have to scratch your brain and to imagine a 4-dimensional space where distances could be negative. So if you have a frame where C is different from 1, you just multiply C squared by T squared by C squared, and the invariant would be X squared minus C squared T squared, or C squared T squared minus X squared. They are both invariant. Let us take the case of some particular case where 2 points, we will take 2 points from the trajectory of motion of a mobile. So if you have a mobile moving, we will take 2 points from its trajectory. So that corresponds to x prime equals 0. The axis, if the mobile is moving on the line x equals vt, x equals vt, which is t prime, corresponds to x prime equals 0. In this case, the distance in the mobile frame is 0, so x prime is equal 0. So the quantity t prime squared minus x prime squared is simply equal to t prime squared, because in this case, x prime is equal to 0. Remember that the 2 points are on the line x equals vt. The line x equals vt corresponds to x prime equals 0. So this quantity is simply t prime squared. But this quantity is invariant. So t prime squared minus x prime squared is equal to t squared minus x squared. So t prime squared is equal to t squared minus x squared. In this case, t prime is the measurement of a clock attached to the mobile that starts from the origin of time, that starts from t prime equals 0, and is measuring the time along the motion. So it is the measurement of a clock that is attached to the mobile frame. This time, t prime, we call it the proper time. It is the time measured in the mobile frame, the clock attached to the mobile frame. In some references, in some textbook, they call it tau. So t prime squared or tau squared is equal to t squared minus x. If you take the analogy to, if you imagine it in a Euclidean space, this quantity t squared minus x squared would be the hypotenuse of a triangle in space-time. Of course, this hypotenuse is shorter than the height of the triangle, or shorter than the other sides of the triangle, because you have the sign minus. Again, I will tell you that you have to scratch your brain and imagine a 4-dimensional space where distances are not straight lines, and the hypotenuses of triangles could be shorter from the other sides of the triangle. When you have c different from 1, so you have x squared minus c squared t squared is equal to x prime squared, which is 0, minus c squared t prime squared, which is also true for differential quantities. So instead of x squared, you take the differential quantity, the smallest displacement in space-time, dx squared. So it holds this equation will hold even for differential quantities. So dx squared minus c squared dt squared would be equal to minus c squared dt prime squared. So you can always use this differential equation. If you take this equation and you divide it by c squared dt squared, you will get dx squared over c squared dt squared minus c squared dt squared over c squared dt squared, which is 1, so it's minus 1, minus, so you cancel the c squared, you will get minus dt squared, dt prime squared over dt squared. If you multiply by a minus sign, so you get 1 minus dx squared over c squared dt squared, which is equal to dt prime squared over dt squared. And you know that dx over dt corresponds to the velocity v. So you can replace dx squared over dt squared by v squared. Then your equation would be 1 minus v squared over c squared times dt squared equals dt prime squared. So your differential of time, of proper time that is measured in the mobile frame, your dt prime, your proper differential time, is equal to the radical of 1 minus v squared over c squared dt. This is the differential time as the smallest step of time as measured in the mobile frame. So the proper time in the mobile frame t prime, or tau as in some references, it is the integral of dt prime. So it is the integral of radical 1 minus v squared over c squared dt. We will use this equation of t prime and we will apply it to a real case. This was the case when Americans did this experiment in the 70s to test if relativity is true or not. They took two identical clocks. Of course, they were synchronized, really synchronized with a ray of light, a real synchronization, two identical and synchronized clocks. One is placed on a satellite, which was in orbit at a height of 100 kilometers with a speed of 1,000 kilometers per hour above the equator, in the plane of the equator, in a circular orbit. And so they put one clock on the satellite, and the second identical clock was kept at rest on the surface of the Earth. And they wanted to see the difference of time between the moving clock, which is attached to the satellite, and the clock at rest, which remained on the surface of Earth. Of course, in this case, the velocity, which is 1,000 kilometers per hour, is a very, very, very small velocity compared to the speed of light. You are comparing 1,000 kilometers per hour to 3 by 10 to 8 meters per second. So it's a very small speed. So your v squared over c squared in this case will tend to 0. And mathematically speaking, if you remember the mathematical courses of the first year, the Taylor expansion and the expansion of 1 minus epsilon, because v squared over c squared is very small, tends to 0. So the radical of 1 minus v squared c squared, it's like 1 minus v squared over c squared. It's like 1 minus epsilon to the power half, 1 over 2. So 1 minus epsilon So the power 1 over 2 is, it's like 1, it's like, if you make the expansion, it's like 1 minus half v squared over c squared plus etc. etc. The other terms are very negligible, so we will take only these two terms, these two quantities, 1 minus half v squared over c squared. So t prime is equal to the integral between t1 and t2, or you can take it between 0 and t, of the radical of 1 minus v squared dt, which is 1 minus half v squared over c squared dt. This quantity is independent of t, so you can put it outside of the integral. So it's the integral between t1 and t2 of dt, which is t2 minus t1. t2 minus t1 is the time measured on Earth by the clock that was kept on Earth. So this is delta t as measured on Earth. So this is the time measured on the frame Earth. This entire equation is the time measured on the satellite, which is t prime. So t prime is equal t2 minus t1 times 1 minus half v squared over c squared. So let us find the difference between the two clocks, the one on Earth and the one on the satellite. The difference is t2 minus t1, which is the difference of time on Earth of 1 revolution. We are seeing the difference of 1 revolution around the Earth. So the clock on Earth measures time t2 minus t1, and the clock on the satellite measures t prime. T prime means that it is t prime 2 minus t prime 1. So the difference between the two clocks is t2 minus t1 minus t prime. So it is t2 minus t1. We replace t prime by this equation. So it's t2 minus t1 times 1 minus half v squared over c squared. You will get a common factor that is t2 minus t1, and the rest would be half v squared over c squared. So what is t2 minus t1 as measured on Earth? If you have a circular trajectory, so it is the distance, the traveled distance, which is the perimeter divided by the velocity. The perimeter is 2 pi times the radius, which is the radius of Earth plus the height of the satellite. If you take approximately the radius of Earth as 6,400 kilometers plus 100 kilometers over the velocity, the speed, which is 1,000. So you use your calculator to see it. So you will find that the difference between these two clocks is around 62 nanoseconds. So the difference between the two clocks is 62 nanoseconds. This is a real difference that was measured in reality experimentally. So with each turn around the Earth, the clock will give you a difference of 62 nanoseconds. So the mobile clock is 62 seconds younger from the clock on Earth by each round, or by each revolution. Okay, I think I will stop for now. We will continue on the next video.